Okay, good morning. So this morning you are going to see how we can discover a whole color picture with potentially a lot of latent variables. Before that, let's finish the previous one. Let's see how we can discover causality from non-stationary data. And this point will be mentioned later today at different levels. So right here, so we have non-stationary data almost all the time. If you measure the data for long enough, then the distribution can change for some reason. So and then, as mentioned yesterday and earlier, causal modeling and the distribution shift or distribution change are heavily coupled, right? Because if you know it's a causal model, you know one process can change without changing any other process, or if they change independently, and so on. So once you have non-stationary data, you have a statistical way to verify the so-called modularity, right? Because they change, then it's a statistical thing. You can just see whether they change independently. And right here, today you are going to see how we can analyze the distribution shift phenomenon to recover causality. And here, by changing causal model, I mean some causal relations, as you can see from here, can be stronger or weaker or even disappear in some cases. Some people may say this is a very good question. Some of you may have this question. In 10 minutes, let me just, this is funny. Let me just talk about it right now. So some people may say the following thing. Oh, I have, for instance, I have X, Y, X, Y causal influence. In one case, right? In one case, basically, suppose we are talking about the brain network. And in another case, I have Y to X. In this case, can we solve the problem? Can we, is it possible for us to discover causality if we have this kind of conflict in the causal direction across different data sets or over time, right? You may want to say so. You may want to ask this question. So the issue is as follows. If you put them together, essentially, you can see there's a way for X to influence Y, and there's also a way for Y to directly affect X, right? So here, and then you have some variable, say some condition right there, right? Corresponding to the domain index or time information. This guy right here will control, this guy, hidden variable, will control the direction between X and Y. Just think of the kind of traffic flow, right? So right here, cars can go this way, cars can go that way, right? And there's one person, basically you can control the direction. Then we'll say, in this case, indeed, this is a two causal graph, right? And furthermore, you have a latent confounder here. It controls both X and how X influence Y, right? Or you can say this controls Y and also how Y influence X. You have a latent confounder, right? So now there's no problem. Basically, in some cases, this one disappears, and in some other cases, this one disappears. As you can imagine, what will happen? What can happen to the traffic flow, right? Sometimes people just go this way, sometimes they just go this way. But if you talk about the causal process, it's possible to have both of them, right? You just have something here to control the both variables and even the causal mechanism or the direction. Yeah.
The C is kind of environment.
Yeah.
Latent, so it says whether which data set to use or
it's correspond to which data set, but it's the physical variable, right? It's not really kind of domain index or anything. But in many cases, we can consider domain index as a surrogate, right? For instance, right now, you can consider time as the index in this case, the traffic flow, right? And then you can say, oh, someone is there, and now go this way. And later go, you can go this way. You can say, oh, some function of time basically controls how, in which direction you can move. Good. So it's just a surrogate. Okay. Good. Now you can see it's unified. There's no problem. So in this case, you would like to answer several questions. You suppose you are given such data. First of all, you may want to recover or determine for which causal mechanism or for which causal modules the influence changes, right? In other words, you are to find the variables for which local mechanism can change. And this is very important because I want to pay more attention to those variables with changing causal mechanisms, right? If they change, there must be some reason. I would like to look into the changeability of the problem. So you may want to find that. As you can see from here, we proposed a framework several years ago, 8 years ago. So here you can see, first of all, you can determine for which variables the mechanism changes. And then you want to find the causal direction compared to traditional methods. Now you can benefit from one more thing, which is the causal mechanism, the causal modules can change, but they change independently, right? So you can verify independent changing condition, and then you can find the direction in a kind of more direct way. And then in many cases, you may want to see why and how, say, X influence Y. You want to see how the causal mechanism changes. What does it mean? We know that we can reflect, we can represent the causal influence of X and Y, the mechanism, with the conditional distribution, right? If the mechanism changes, then conditional distribution must change. Then essentially, in this case, you just want to find a low-dimensional representation of the whole conditional distribution of this variable given its parents, because the conditional distribution of this variable given its parents denotes the generating mechanism for this guy. You just want to see how it changes either over time in non-stationary case or across different data sets in the heterogeneous case, right? It looks kind of complex. Actually, it's quite simple. Why? Because no matter how complex the conditional distribution is, you just want to find the representation. You can use kernel embedding, you can use anything. And then you want to find low-dimensional representation to preserve the variability of the conditional distribution. So we developed a method called kernel non-stationary, right here. Kernel non-stationary driving force estimation is just a some kind of extension of kernel principal component analysis to preserve the changeability or variability together with some embedding to represent the conditional distribution corresponding to the causal mechanism. Okay, so basically you can see how you can solve the problem. First of all, you have surrogate, you have domain index or time index, and then you can show, you can prove that as long as this variable is always dependent on C, the index, then for this guy, the mechanism must change. And then you can find the direction with independent noise, independent changing condition, and then you can just find this with the kernel trick or with some non-primary method, you can figure out how the causal mechanism can change. Okay.
Question?
Yeah.
Can you go back to?
Yeah.
I mean, the nodes have this thing on it. So what it mean? There's this red thing on node.
Oh, that means it's just a notation. So it means that for this guy, the generating process or the local causal mechanism changes.
So you know that they are.
Oh, you determine that.
You determine.
Yeah, this is the first step. You can determine that from data. And it's not about whether distribution, this guy, the distribution changes. It's just about local causal mechanism. Let me give you one example. Suppose here X changes. As time goes on, something say X is influenced by temperature, but you don't measure temperature. Clearly, this guy will change, right? And suppose X influences Y. Then, of course, generally speaking, the distribution Y will also change, right? But here, you can figure out that, oh, only I know that the fundamental change happened to X. This part is still invariant.
Y given X should.
It's still invariant, yeah.
So then the goal is to find this invariant.
Find everything. If it's invariant, then we know it. If this guy also changes, I also know it. So this is one thing, C1, C2. I can discover the whole picture from data with multiple distributions. Good.
Just a quick follow-up. So does that effect changes? Let's say if it's linear, does
Mhm.
the effect between X and Y also change across
Oh, yes, good. In the first example, it does not change. You only have a change here, as you saw from next slide. So maybe I should use this slide. So right here, you can see, let me give some examples. Here, you can see V2 changes clear because you have something, right, with the C, the index as a surrogate to change the mechanism of V2, right? Right there. However, for V3, clearly the distribution will change because V3 is influenced by V2, right? At the same time, you can know that this guy does not change if it's really the case. Furthermore, even if this guy changes, you can still discover the causal direction, and you can say, oh, here, this guy must change as well. And that's an example for this one. For V5, you can see V4 changes. And V5, for V5, the mechanism also changes. You can discover that part as well. So essentially here, you can discover all the direction. And then from this graph, you know, V1 is stationary because V1 is not changing not changed by anything. And then V2 changes, and the change in V2 and the change in V4 given its parents, and the change in V5 given its parents might be related. They may have a latent confounder. And latent confounder is a kind of function of the, say, time or domain index is as a surrogate. And furthermore, from this graph, you know, although V3 changes, the conditional distribution of V3 given V2 is invariant. Okay, so all those things can be discovered from data.
But the conditional distribution of V5 given V4
Also changes. Yeah, also changes. That's why you have this, as long as this guy is adjacent to this guy, that means given anything, they are conditionally dependent, meaning that, oh, this one must point to this guy, meaning that this kind of surrogate must be part of the causal mechanism, right, for that guy. So the mechanism will change. Good? Okay.
So model can tell us whether or not the variable changes conditional on the others. Can it to tell us to what extent they change among them?
Yes, exactly. That's the this part. That's the visualization part. So essentially, like in the linear case, it's kind of trivial, right? You can find a linear model, you can try and estimate coefficient, noise level, and so on. But generally speaking, you just want to find a way to preserve all the information of changes in the mechanism, right? So that means you want to find a function of the condition, suppose VI, the mechanism for VI given its parents changes, and then you want to find a low-dimensional representation to preserve all the change information in this conditional distribution. That's exactly what kernel non-stationarity visualization does. So right here. Yeah, later you can see some examples. Yeah.
It's similar to a hidden confounder.
Oh, good. Right here, actually you can say GC. This is the true confounder, latent confounder. And for instance, right, temperature can directly cause a lot of things, right? But if you don't measure temperature, probably time is a surrogate. So in that case, you really have a latent confounder, but you don't know it. That's why it's latent confounder, right? So here in this work, we assume that yes, there could be latent confounders. However, the latent confounders can be written as functions of some surrogate. That's why it's kind of greatly simplified everything. And in very many situations, that's good because we know, yes, some situation or background variable can change across data sets, right, or over time. Then you will have to make use of such information. Later today, you are going to see that in many other situations, we don't need this assumption. So you can always have a lot of other latent confounders.
Surrogate of observed.
Exactly. Surrogate is like kind of domain time information, right? Domain index on the first day of the class, second of the class, 1, 2, 3, 4, right? So you have the surrogate information. Yeah.
So this kind of using this mechanism over there for the GLC of the changing point, it actually can make a prediction of a changing point for one system interaction and another system.
Yeah. Yes, that's true. If you have this representation, you know how it changes, right? And then later you see, I will give you an example. Cool. Now let's finish this part. As long as the basic idea is clear, it's wonderful. So here, we want to make use of independent change property in the conditional distribution of the causes, appearance, and the conditional distribution of the effect given causes. So this is clearly a generalization of the traditional invariance notion in causality. So basically, there are two kinds of invariance. In one of them, we have invariant cause. Basically, it says following thing. I have C here, I have VK, VL, they are adjacent, and I know this guy go to this guy. So basically, this is not a wave structure. Okay, I apply PC, for instance, to the data with C as the additional variable. I discover this pattern, and this is not a wave structure. What does it mean? If that's the case, we know that we assume the surrogate, right here, we have either latent confounder or some driving force of the change, right? So this guy will be a cause. In other words, C will go to this variable, right? C will go to this variable. Then we can do orientation propagation. The direction between VK and VL will also go this way. Otherwise, we are going to have a fake wave structure, right? If you have that, what does it mean? Oh, yes, that's the second case. So suppose this is not wave structure. In the first case, it's a wave structure. So then you have this case. What does it mean? It means that something related to the time or domain, right? A non-stationarity indicator will change the distribution of VK, but this part VL given VK will be invariant. Since VL given VK is conditionally independent from C. If something is conditionally independent from C, what does it mean? It means here. It means the following thing: P, V, I should have used that. VL given VK and C would be for different values of C is the same, right? For different value of C is the same. That means it's invariant, right? So here, basically, you can think of invariance as a particular conditional independence relationship. If they are conditional independent, C, VL independent given VK, then it's equivalent to you have invariance, as you can see from here. This is an invariant mechanism because no matter how you change the cause VK right here, the causal mechanism from VK to VL is invariant. This is a traditional in one type kind of traditional invariance. This is invariant mechanism. And in contrast here, you may have a wave structure. If you have this guy, what does it mean? It means that VL does not change because VL is not adjacent to C, but VK is adjacent to C. Then this is a wave structure because they are independent. This is a wave structure, right? They are independent. They are not independent given this guy. So this is a wave structure. And then we know that VL go to VK. At the same time, we also know that VK conditional on VL, the conditional distribution of VK given VL will change, right? Because clearly condition on VL, VK is dependent on C. That means for different values of C, the conditional distribution of VK given VL can be different. That means the mechanism from VL to VK can change, right? At the same time, you can see the distribution of the cause of VL is the same. This is a invariant cause. I can give examples here. So suppose you just in the we know rain causes the wet ground. Rain causes the wet ground. Wet ground. So suppose in the first case, regarding invariant cause, suppose you still actually stay in the same region right here, but you may just go from one, say, from the, you may just kind of stay in different places, right? And in one place, actually, I will stay indoors most of the time, and in another place, I will stay outdoors most of the time. Then the conditional distribution across the two scenarios of the wet ground given rain will be very different, right? Because in one case, I mainly stay indoors, and in the other case, I will be outside. Then the conditional distribution will be very, very different. However, the probability of rain or the distribution of rain across two small places would still be the same, right? So the invariant cause, but the mechanism can change. And furthermore, let me give another example now to illustrate the second point. Disease causes the symptoms, right? So if you travel in different areas or in different countries, the probability of the disease can be very different, right? Because of tradition, because of medical condition, and so on, right? The distribution of disease will be very different. However, the conditional distribution of mechanism of symptoms given disease will be roughly the same, right? Because basically we are human beings and we share a lot of features. Say you can see examples regarding invariance. However, here we can go beyond that. Even if both of them can change, so C can also go there, then we don't care because we can still verify whether the mechanisms change independently, as you can see from here. So if you have this case, then this is the invariant mechanism. If you have this case, you have invariant cause. You may have this, right? Because the cause distribution and the mechanism can change at the same time. However, they change independently because of the modularity property, right? And according to Pro, causal system is autonomous. There are no relationship between them. You can verify whether they change independently. Okay, so this is the kind of generalization of the invariance in causality, and then you can find the direction. Good. I need to finish this part as soon as possible. Okay. I already talked about this. Essentially, just found one. You want to find low-dimensional representative conditional distribution. You can see how it changes, as you see from here. And this is the result on the kind of Hong Kong stock market. Right here, with this method, you can avoid a lot of links. If you compare this method with the PC, you avoid a lot of links. And it's interesting because those links mainly happen between stocks in finance and stocks in properties, right? So basically, both of them are very sensitive to policy. There could be policy, could be a common cause, latent confounder, right? Because we don't have policy right here. However, now you can remove such a thing. And furthermore, you can find the direction. And you can see for all those nodes in red, the mechanisms change over time. As you can see from here, we visualize how they change. For 2, you can see right here, 2 is here. The conditional distribution of 2 given its direct causes 7 and 10 changes. And actually, this is the T2. This is right here, 2008. And this is 2007. And this is, I skipped right here. This is the curve of TED spread. It's a kind of measure of the risk in the market calculated in a very complex way. Okay, now you can see they are really similar to each other, right? So essentially, we analyze only the daily returns of the stocks, right? Only that. But we find the direction and we find why and how the generating process for one stock return given the parents can change. And then you can see, now I see this is financial crisis. Actually, this is some kind of risk. It's very long, the life is long, right? And now you can see in 2007, the risk was already very long and it lasted for quite some time right here. So you can really discover why the causal mechanism can change. Essentially, it's a specific type of risk associated with a particular company, right? And this is the risk in the total market, in the whole market. You can recover such information. Risk or our kind of perception of the risk clearly is the cause of the generating process in the stock market. Okay, and then I will skip this result. We also analyze more than 80 stocks in New York Stock Exchange. You can see similar things. Good. So you just saw how we can deal with latent confounders in one way, in which we don't really care very much about latent confounders. We try to focus on the causal relation among the measured variables, right? Later, you can see how we can also focus on latent confounders or latent variables. You can see how to deal with cycles, non-linearities, memory error, selection bias, missing values, and so on. Those things basically are kind of almost complete, right? This list is almost complete. So in reality, if you have data, remember, in causal discovery or causal representation learning, you want to recover the truth. That's why we have to care about how the data is sampled, right? And whether there's noise and so on. But basically, the problem can be solved. So in reality, if you have a real problem, look into the problem. There might be a lot of kind of other factors, right? You have to consider, and then after you consider those factors, it is very likely for you to discover the underlying truth of interest. Okay, so now let's see how we can learn latent variable and their relations. In this part, we can make it a little bit more kind of interesting. I will talk about the picture in our former students, Dr. B.W. Huang, who is an assistant professor at UCSD. We'll talk about one method, and Yujia will briefly talk about some other method. And Xinshui, if you like, you may say something about the new result. Basically, you can see how this field is quickly evolving. At the same time, this story is far from complete. However, here we mainly focus on how to discover the whole hidden world without making use of interventions. In contrast, a lot of other researchers, including Francesco Luctella, Caroline Wooler from MIT, and Bernard Schalkopf, and Sarah Medican from Netherlands, are doing causal representation learning, and usually they assume that there could be some interventions. So you can apply interventions, and then you want to find a causal representation. In this part, we mainly focus on the setting in which you don't have any interventions, or you don't observe any intervention. You only observe the data. Okay. Okay, so basically, you see why we care about that. And when we say disentanglement or disentangled representation, what do we mean by that, right? And here, our point is that when you try to find a disentangled representation, actually, you want to say that this representation is an important thing in the underlying process, okay? And you can see how, and you can see how we can do it in different cases. In the ID case, from multiple diffusions with temporal information and so on. So you can see how we can solve the problem. Okay, it's coming. So in causal representation learning, we mainly focus on high-level latent variables, right? For instance, you have images. Image pixels are clearly related if they are close by, right? This kind of dependence, you can see this kind of dependence not because they are directly causally related. Instead, there are some kind of high-level latent variables, right, like concepts, so that they are related. So we aim to find such latent variables and their relations. You just want to recover the truth. Although it's hidden, it's part of the world. And in disentangled representation learning, some years ago, people just tried to achieve independence among the representations. So that's why nonlinear ICL, some kind of nonlinear ICL was very useful. However, in practice, you can see very oftentimes the underlying latent factors of interest might not be independent, right? One may cause another and so on. But still, as long as there are important things involved in this causal generating process, you may want to recover them. So disentangled representations are not necessarily independent, right? As long as they have a meaning, right here, and as long as there could exist a way for you to directly change that guy, it's a disentangled representation because it's a part of the causal process. Okay. So how can we solve the problem? You saw this picture. This is the third time to show the picture, and Peter's Rated also showed this picture. So essentially, we make use of modularity property. Okay, and then from modularity property, you can easily derive a number of properties, statistical properties, including condition independence, independent noise, minimal change in the causal representation, and if they change, they have to change independently. So in minimal changes and the property of minimal changes and independent changes in the causal representation. We can make use of all of them to solve the problem. Okay, So you saw how we could do causal discovery. Now we've mainly focused on how to recover the latent variables. But from my perspective, we don't have to really distinguish between causal discovery and causal representation learning, right? You can consider one of them as a special case of the other, because in both of them, you just try to recover the underlying true causal relations involving with or without latent variables, right? We consider 3 dimensions of the problem because we have to see how we can really investigate the problem. So the first dimension or first axis right here is what kind of data you have. In some cases, we have ID data. For instance, we just in the archaeology analysis scenario, we only have data points generated from some distribution, right? We can just say, oh, it's ID data. I try to infer information of the distribution and I try to recover the causal relations. And in some other cases, we have non-ID data, right? So you have you measure something in day 1 and then measure the same things on day 2 and so on. And then you have multiple distributions. It's very often time you can see the distribution can change across the scenarios or over time. You have non-ID data. And by non-ID data, I mean, you may have temporal information, right? Or you may have multiple distributions. And for causal representation learning, you can easily make use of the additional information, right? By additional information, I mean either temporal information or change in the distribution. In some cases, you may have parametric constraints. In some situations, you may assume the system is linear. And then clearly, this kind of assumption can greatly reduce the search space, and you have more informative result under weaker conditions involving other things, right? Other dimensions. And the last thing is whether you allow latent confounders. For causal representation learning is trivial because we always allow latent confounders since we want to recover them. But overall, if you put them together, so this is also another dimension, because in some cases, without latent confounder, you have guarantee. And in some cases, even if you have latent confounder, you still have guarantee, right? By the way, here, identifiability is so important. Without identifiability, we cannot say we are doing causality, right? Here you can see a summary. You saw those parts before. ID data with latent confounders. Say here you can use PC. You don't allow latent confounder. You can use PC. You have equivalent class. And with even if you allow latent confounder, you can use FCI. You have another kind of representation of the equivalent class, right? And here you have parametric constraints. And you don't allow latent confounders. You have, for instance, you have linear non-Gaussian methods, right? And you can even allow latent confounders. You can still recover some information of the causal picture. For instance, I talk about overcomplete ICA-based method, right? Even if you have latent confounder, you can do something. And if you have a traditional time series, you can, under some assumptions, granular causality is true causality, right? If there are no latent confounder, and if you measure the data in the right way, at the right resolution, then granular causality is nothing but time-delayed true causality, right? So you have non-I, means that ID stands for independent and identically distributed sample. So the first I is independent. You have dependence, but still you have a fixed distribution. So this is time series case. And you can think of a granular causality, and then it's basically just extended regression. And later you can see, if you allow a lot of latent confounders, you can do many things. I will give one example. Basically, you can learn the latent temporally related causal processes from the observations. So from video data, you can try to understand what's going on by automatically discovering the underlying objects, concepts, and their relations. And in the second case, you have a violation of second I. Basically, you have multiple distributions, and you can see how we can go further. Okay. Okay. Oh. So let me introduce the problem here. We have data sets, as you can see from here, we measure a lot of answer scores, right, to the questionnaires. And we try to look into the problem, look into the mental conditions. The mental conditions are clearly hidden. Generally speaking, they are hidden, right? Because you cannot directly kind of open somewhere and then say, oh, this is the one dimension. It's right now, at least, we don't know it. Probably in 20 years, because of these kind of studies, you know what exactly you mean by personality, and then you can go there and assess it, and probably can also change it, although it's crazy. So here you want to analyze the measured variables, and you try to infer the latent variables, as you can see from here. So in 2 minutes, Professor Huang will talk about this part. And now let me just say a few words. First of all, he will talk about the low rank condition or rank deficiency method. This is the basic idea. So here, this is latent variable, L6. Then you can see the cross covariance matrix between say X10, 11, and all the rest will have rank 1. Because one variable can just separate them. Then the cross covariance matrix, this is not a covariance matrix, this is a kind of sub matrix of the covariance matrix, right? It's a covariance between X10, X11, and the rest. It's a cross covariance matrix. Then the rank will be 1. Okay. Think about it. So this way, with some kind of specific procedure, you can determine whether you have latent confounders and where they are. Okay. And furthermore, there are number of questions. If you allow this guy to be measured, suppose this is also measured variable. Now you can see this picture could be very messy. Measured variable could be here, hidden variable, measured variable could be there, and so on. So it's completely flexible. Can you solve the problem? Can you still use the rank deficiency condition to solve the problem? Basically, this was done by Xinshui and Biwei recently. So you can still recover the whole picture, even if it's so flexible. Okay. And later you can see in the linear non-Gaussian case, you can make it even more flexible. In the linear non-Gaussian case, we even have the necessary and sufficient conditions on the graph so that it's recoverable from data. Well, now, Biwei, are you there? This is the linear non-Gaussian case. Right here, you can see if you have 3 measured variables, all those graphs involving latent variables right here are identifiable. Given here are identifiable, and only those graphs are identifiable from the measured value of the 3 variables x1, 2, 3. It's completely free. You can see you can have inference from measured variables to hidden variables. You can have inference from hidden variable to measured variables. You can have a relation in between, and so on. In the linear non-Gaussian case, you have necessary and sufficient condition to verify whether graph involving latent variables and complex interactions can be recovered from data. But in the linear non-Gaussian case, unfortunately, in this case, we don't have an efficient method. Later, you can see with some kind of specific technique, you can solve the problem when some additional assumptions hold true. Okay. And you can even recover this kind of deep structure from data given the measured variables, right? You just construct latent variables step by step, you can recover the whole picture. And even if this guy is measured, you can still recover the whole picture because of work. Okay, oh, yeah, there.
Yeah, I'm here. Hi.
Can you say something? I cannot hear you.
Hello, hi Kun, can you hear me?
Still, I cannot hear you. Maybe there's some problem right here.
Yeah.
By the way, thank you very much for getting up so early to give the lecture.
Sure. Thank you for having me.
Can you try? Oh, I can. Okay. So Guanyin said he could hear Biwei, so we have a problem here. Wonderful. There are no problem on your side.
Yeah.
We just wait a while. Yeah. Yeah. And you can see the condition in this paper. Oh, it's annoying. Go away. So identification of partially is very long. Partially observed linear causal system, blah blah, graphical conditions. So essentially, it's in the most general case, you can see I really have a true causal picture right there, but unfortunately, I only observe some of the variables, no matter where they are. Under what condition can I recover the whole picture? That's the problem. Oh, can you say something?
Hello, hi Kun. Hello,
Say
everyone.
something. Let's wait a little bit.
Yeah.
You can say something?
Hello.
Wonderful.
Hello.
Genius.
Oh, great. Thank you so much.
Would you like to share screen, or would you like me to play a slide?
May I share the screen?
And then probably we have to adjust our kind of break time for the break. Then we can finish this part first to
Yeah,
make it.
yeah, sure.
Sorry, it's my problem.
How long will I have? Maybe 30 minutes is okay. It's
40,
okay for me.
Around 30, 40. So
Okay.
flexible later, I can see how long or short the time is. So you can, okay, now we can see your screen. Please go ahead.
Yeah, hi everyone. Thank you for Professor Kun having me. So it's great to meet you. Or sorry, let me, my screen sharing is paused. Let me share again. So you cannot see the change on my screen, right? Hello, hi Kun. Can you see the change on my screen?
You may want to share the whole your desktop rather than the application.
Okay, sure. Okay, good. It works now. Thank you.
Yeah. All right.
Yeah. So basically, in the following half an hour, may I start now?
Yes. Please go ahead.
Okay, thank you. Yeah. So in the following half an hour, I will introduce our method for identifying latent causal graphs and models in the linear Gaussian case. So let's first see the motivation. So for causal discovery, we aim to find causal relationships from observational data without doing interventions, because we know intervention is so computationally inefficient and may not possible in some cases. And traditionally, in most classical approaches in causal discovery, we only consider causal structure among the observed variables and assume there are no latent variables. And I believe you have already learned a lot from Professor Kun's lecture on learning the causal structure between observed variables. However, in many cases, our measured variables may not be the causal variable. For example, if the measured variables have measurement error, and or if for images, we cannot directly treat the image pixels as causal variables. So in this case, how can we find the underlying causal variables and the causal structure? So correspondingly, let's look at this let's look at these example graphs. Here, X are the measured variables, and the L indicates latent variables. So you can see that there are direct causal relations among the latent variables, and we have causal relations from the latent variables to measured variables. Now we have two questions to answer. First, give you only the measured variables. How can you locate the latent variables here? Or in other words, clustering the lower level variables. And furthermore, how can we identify the causal structure among all those variables? So these are the main two questions we want to answer in particularly in this work. So before introducing you the detailed techniques, let's first see the motivation of latent variable discovery. Why we want to learn the latent variable discovery and how will it be useful in AI and scientific discovery. So we know that usually in practice, it's not possible to measure all task-related variables. So there are always some, in most cases, there are unmeasured factors that influence our observed variables, and directly ignoring such variables may lead to misleading results. So it's very important to to consider causal discovery when there are latent variables. And moreover, when giving you like unstructured data like images, videos, or languages, so basically we want to extract the underlying concepts or causal variables or the hidden causal variables, which can help us a better understanding of the images or videos or languages. And furthermore, this extracted underlying concepts or causal variables will be essential for downstream tasks, such as prediction, decision-making, and so on. And moreover, like in neuroscience, from our measured fMRI voxel data, we want to automatically identify and hierarchically cluster the underlying functional brain regions, and also discover the information flow among different brain regions. And nowadays, we know that these regions usually are predefined, but we want to do it in an automatic way to find information that our humans may not know in advance. And also in biology, we want to identify gene regulation process from gene expression data. And we know that it's very important to identify the gene networks that are responsible for certain disease, which can help us to find a better treatment. Okay, so these are the several motivations. Okay, now let's see a classical technique that is used for latent causal graph discovery, which is called tetrad condition. And tetrad condition is initially developed by Sperman more than 100 years ago. Okay, let's see an illustration. Suppose now we have these two graphs. Here, X are the observed variables, and L are the latent variables. Now, given you only the measured variables X, how can you distinguish between these two graphs? Okay, let's use rho ij to represent the correlation coefficient between two measured variables, xi and xj. Now let's first see the left graph. From the left graph, we will have the following equality and inequality. So we will find rho 1, 2 times rho 3, 4 doesn't equal to rho 2, 3 and rho 1, 4. But for the right graph, we will have such equality. And similarly, in the left graph, we will have rho 1, 2 times rho 3 doesn't equal to rho 1, 3 times rho 2, 4. But the right graph holds the equality. So we can see and we call this tetrad condition. So basically you can see by leveraging the tetrad condition from the measured variables, we can distinguish between the two graphs, even if we didn't observe the latent variables error. And actually, tetrad condition indicates the rank deficiency of 2 times 2 off-diagonal covariance matrix. So tetrad condition is indicates part of the information from rank deficiency of the cross covariance matrix. And later we will see how we make more use of rank deficiency to identify more general latent graphs. Okay, so here's applications of tetrad conditions to some types of latent graphs. One is called one-factor measurement model, and the other is called a tree. So basically, for the one-factor measurement model, for every measured variable, it should only allows to have one latent variable. And at the same time, in most of the methods, each latent variable should have at least 3 measured variables. And for the tree graph, it assumes that for every pair of variables, there should be only one and at most one path. So you can see with tetrad condition, we can only allow very simple latent graphs. Now we want to see how can we identify more general latent structures, because in practice, in most scenarios, the latent structures could be more complex than the one-factor measurement model and then the tree. So in this work, basically, this is our work published last year in Europe. So we want to make a better use of rank deficiency constraints to identify more general latent structures. Okay, let's first see a big picture. So in this work, we assume like each variable satisfy a linear function causal model, no matter for whether it is for measured variables or for latent variables. And here from these are 2 example graphs. For this graph, you can see that we allow the latent variables satisfy a hierarchical structure, which means that the children of the latent variables can still be latent, such as L1 and L2, L3 here. So the children of them are still latent. And then we allow multiple passes between every pair of variables. For example, let's look at L6 and L7. So there could be multiple passes between them. Okay, so now we have, so for this kind of graph, we have 2 questions to answer. I just repeated questions. So first is, given the observed variables X, how can we locate the hierarchical latent variables? Or in other words, clustering the lower level variables. So basically we want to see which observed variables should be in the same cluster. For example, for X1, X2, and X3 here. They are in the same cluster covered by latent variable L6. And moreover, we want to know how we want to identify the causal structure among latent variables and from the latent variables to measured variables. Okay. Okay, here's a basic idea, and Professor Kwon already have mentioned it. So basically, in this work, the basic idea is as follows. We make use of rank deficiency constraints over the measured variables X, and together with certain search procedure to identify the latent variables and to identify the whole causal structure. And we make use of this rule, which is a foundation of this method. So let's denote XA as a set of measured variables and XB as another set of measured variables. So basically, if the rank of the cross-covariance matrix of XA and XB, if it is deficient, then it indicates the smallest number of variables that separate XA from XB. So this is the most important rule we use to identify the graph. So it's very important. Let's see this example. Let's suppose XA contains X10 and X11, and XB contains the remaining variables. And now, if we check the rank of the cross-covariance matrix of XA and XB, we will find that the rank is 1, and it is rank deficient. This is because L6 separates XA from XB. So you can see here, L6 separates XA from the remaining observed variables. Okay, so basically we make use of this information to locate the latent variables, determine their cardinalities, and identify the until causal structure. But notice that here we cannot directly know the location of these latent variables by locally using the rank deficiency constraints, which means that we need a certain search procedure, need a specific search procedure in order to identify the whole graph. Okay, here's the main search procedure in order to find the graph. So the input is the data from a set of measured variables, and the output is the Markov equivalence class over all the variables, both measured and latent. And it contains 3 main steps. In the first step, we aim to find the latent clusters, and assign latent parents in a greedy way. We call the first step find causal clusters. And in the second step, we characterize and refine some incorrect clusters due to the greedy search from phase 1, which is called refined clusters. And finally, we refine edges and find the V structures. Okay, let's first see step 1, find clusters and assign latent covers in a greedy way. Okay, let's suppose now we look at this ground truth graph on the top right part. And for phase 1, we make use of this rule 1. So if A is the rank deficiency set with rank over XA and XB being K, then we assign a latent variable air with size K as a parent of each AI. So this is the rule we make use of in step 1. Okay, now let's see the procedure. So we first input the data from measured variables X. And now which let XA contains X5, X6, and X7, and XB contains the remaining variables. Now we check the rank over XA and XB. We find that the rank is 2, and it is rank deficiency. So we add the latent cover R6 prime and R7 prime with size 2 over the cover XA. Similarly, in a similar way, we can find the latent covers R6, R7, R4, R5, and R8, R9. Okay, now furthermore, now we have latent covers. Okay, from this step. Sorry. So basically, now from this step, we already have covers R6, R7, R8, R9, R4, and R5. Now we check the rank again by from these root variables. Okay, now let XA contains R4 and R5. Since R4 and R5 are unmeasured, we instead make use of its measured descendants, XA. So XA are the measured descendants of R4 and R5, and XA contains X1, X2, X3, and X4 as a surrogate for rank test, which means that we always only make use of the data from measured variables. We don't need to directly estimate the values of latent variables, because in this way, the error from formal estimation may propagate when we go to very high level of the structure. So we only use the data from measured variables. And now we test the rank of XA and XB, and we find the rank is 1, and it is rank deficiency. So we add the latent cover R2 with size 1 above A. Okay, that's how we find the latent cover R2 over R4 and R5. And in a similar way, now let A contains R6 and R7, and we use its measured descendants XA, that is X5, X6, X7, and X8 as surrogate for rank tests. And now in this case, we find the rank of XA and XB is 1, which is rank deficiency, which is rank deficient. So we add a latent cover L3 with size 1 above L6 and L7. That is how we find the latent cover L3. Okay. Now, and finally, for this, now we can see, finally, we cannot find a more, like, we repeat this procedure until we cannot find any more rank deficiency set. And finally, we connect those covers into, and the step 1 ends. Okay. So now in the same step, we realize that in some specific cases, the find clusters in step 1 may not be correct. Because some small clusters may be merged during the gradient search. So in the second step, the main goal is to characterize what kind of clusters may be wrong and further refine such incorrect clusters. And basically from the first 2 steps, we can make sure that the learned clusters are all correct. Okay, now let's see the details of step 2. Okay, now you can see this is our identified structure from phase 1. Okay, now what we want to refine refine the incorrect clusters, and by making using of rule 2. So basically, rule 2 says that for each discovered latent cover L, let V contains the grandparents, siblings, and the children of L, and apply find causal clusters, that is step 1, to V to refine the clusters. Okay, let's continue to this example, to see this example. The pink area indicates the incorrect clusters due to the gradient search in step 1. Yeah, we can quickly compare it to the ground truth graph. You'll see, right? You'll see it, right? So the pink areas are different from the original graph. Why this happens? This is, you can see that actually, like if we look at the latent cover L3, it should be X11, L6, and L7 form a cluster. But due to the gradient search in step 1, we incorrectly cluster X10, X9, X10, and X11 together. This is because at that time, we haven't identified L6 and L7 yet. And due to the gradient search, so we first cluster L9, X9, X10, and X11. So now we want to refine this cluster. Okay, so let's see the procedure. So we first refine L2 by removing L2 and its parents, L8 and L9. Okay, now this is a graph. Now we perform find clusters over the current root variables, that is L3, L4, L5, X9, X10, and X11. And then by applying step 1 find causal clusters over these root variables, we will find the latent cover L10. Okay. And furthermore, we perform find causal clusters, the step 1 over the current root variables L10, L4, L5, X9, X10, and X11, and then we can find the latent cover L11 here. And similarly, we can find L12 here. And finally, we connect, if we cannot further find rank deficiency, we've connected the latent covers. Okay, now we finish the refining of L2. And similarly, now we refine L3 by removing L3 and its parents. And we perform find causal clusters, the step 1 over the root variables. And we can find L13. And finally, we connect those root covers. Okay. So yeah, this is step 2. Now we can see, let's compare this final graph to the ground truth. We can see now they have the same skeleton, right? They have the same number of latent variables and have the same skeleton. Okay, and in the final step, we refine the edges and find the V structures. Okay, this is step 3. So basically, you can see we can refine the edges and find the V structures. And in this example, there's no V structure. And we have the here we have the direction from air to X, because we always assume it is from the edge is from the latent variables to the measured variables. So in this step, we can refine the edges and finally output the Markov equivalence class. Okay, so yeah, here I give another example to better show our phase 3. How can we find the V structures? Okay, now let's suppose this is a ground truth graph, which contains V structures. So you can see here, Air2, Air3, and Air4 forms a V structure. And this is one possible output from phase 2. Okay, now let's check the V structures. We first connect Air2 and Air3. Now we check the following things. Let A contains Air2 and X1, and B contains Air3 and X2. So basically, we know that if the air variables are observed, we can use D-separation, right? So Air2 and Air3 are D-separated given Air1, but now they are all unmeasured, they are all latent. So how shall we do? We split the children of air variables into 2 parts, so X1 and X2, and put X1 in A and put X2 in B. Okay, then we check the rank over A, the covariance matrix over A and B, and we find the rank is 1, which is deficient. It means that Air1 separates Air2 from Air3. So we can remove the edge between Air2 and Air3, and we know this cannot be a collider. Okay, and furthermore, we want to find the collider Air4. What shall we do? Let's first let A1 contains Air2, Air4, and X1, and B1 contains Air3 and X2. So basically, the difference of A1, B1 is that compared to A and B is that now we can see we additionally add Air4 into A1, which is a difference from A and B. And now we tested the rank. We find that the rank of A1 and B1 is 2, which is larger than 1 and is not efficient. So which means that is the rank is larger than the rank over A and B. And similarly, now let's construct A2 and B2. And in here, we put Air4 into B2 instead. And we check the rank again. And we find the rank is 2, larger than the rank over A and B. So we can know here there's a V structure and Air4 is a collider. Yeah. This is our main the rough procedure, how we decide whether there's a V structure or not, by making using of the different types of rank tests. Okay, now here's the main identifiability condition in this work. So basically, for each latent variable set with size k, then in order to achieve identifiability, it should have at least k+1 pure children, which can be either latent or measured, and another k+1 neighbors. So here for pure children, we mean that if V are pure children of a latent variables air, then V don't have other parents besides air. So which means that air are the only parents of V. Let's see an example for this condition. So let's suppose air contains Air2 and Air3 with, so you can see the size is 2, so k equals 2. Now we can see it have at least 3 pure children for example, let's suppose AR6, AR7, and AR8. And it has additional 3 other neighbors, AR10, AR9, and AR1. Okay, so which means that this structure satisfies the identifiability condition. Yeah, so basically, let's make a quick summary. So basically, this approach works for latent hierarchical causal structure with linear causal relations. And each latent variable set with size k should have at least k+1 pure children. And we also allow multiple latent parents for each measured or latent variable. So you can see in this work, this work allows much more general latent graphs than, for example, than the one measurement model or the tree structure. Okay, now let me, so we recently have an extension to more general case that can, here, now we further allow observed variables to be causes as well. So this is our ongoing work done by Xing Shuai, P.S. Kun Zhang, and many others. So now you can see in the previous work, we only allow direct causal influences among latent variables, right? We don't allow the direct influences among the observed variables. And in practice, it's hard to say. It may be the case that we may have direct causal influences both between the latent variables and between the latent observed variables. So basically, this work actually provides a very general framework for causal discovery in general cases. And in the spatial case with no latent variables, we just return the same graph as the PC algorithm, which is designed for observed variables. Okay, so here in this work, basically, we allow causally related variables as well. So the latent variables may form a hierarchical structure as the work we just discussed. And now, furthermore, the latent variables can serve as both confounders and intermediate variables, or can serve as just both causes and effects for the observed variables. For example, here, let's see AR2. Let's look at AR2. So here, A are the latent variables, X are the measured variables. So AR2 are the confounders, are the causes to these observed variables. And it is also the effect of the measured variables X. And see, now it's very general. We can allow the latent variables almost everywhere, except the leaf nodes. So if the latent variables is in a leaf node, then it doesn't make sense. We don't need to consider anymore, and will not affect our results over the entire causal graph. So it's fine. Okay, let me briefly discuss a technique we use, why we can handle direct causal influences among the observed variables as well. So that is why we can also allow the latent variables as an effect of the latent variables. So basically, we make use of this rule. So which also gives the relation between dependence and rank constraints. So suppose A, B, C are the disjoint subsets of all the variables. Then the conditional independence statement, XA and XB are independent given XC holds for X, if and only if the rank, this rank, so basically the rank over, so the left part is the union of A and C, the right part is the union of B and C. Then the rank of this covariance matrix has rank C. So yeah, basically these are equivalent. So we can make use of this condition to allow a more general causal discovery framework. So here we know that if all variables are measured, then we can just output the same graph as the PC algorithm. And if there are no direct causal influences among observed variables, then it's just output the same graph as the work we just discussed. So it's very general. Let's quickly look at an example. Let's suppose, okay, this is the ground truth graph. Okay, now we start the search procedure. So we first find that if we take x equals x3 and c equals x8, and here we test this rank, and n represents the remaining variables in the current active set, then we will find that this rank is 1. So we add an age from x3 to x8. And furthermore, if we take x equals x2 and x3 and c equals x7 and x8, we find the corresponding rank is 2. Okay, so we add an age from x2, x3 to x7. And further, we check, we take x and x equals x2 and c contains x4, x5, and x6. We check the rank, which is 2. So we further add these ages and add the latent variable L2. And furthermore, finally, we can identify the whole graph. I believe maybe Xingshuai will give you more details about the procedure later. Yeah, here I just give a very brief picture. Okay, here's some experimental results. We compare the F1 score. So we consider several different cases if there are only observed variables. If the latent graph satisfy a tree structure, if a latent variable satisfy a measurement model, and if for latent general structures. And so for example, in case 1, if observed only, we compare with a PC algorithm. And interestingly, we find our methods is much more robust than PC algorithm. Yeah, okay. Yeah, here's a very interesting result done by Xingshuai, the big 5 questions. Yeah, yeah, we have very interesting findings. So first, we find that our findings corresponds to the big 5 concepts very well. And furthermore, we find that some parts can further have more detailed structure beyond the just 5 clusters. Okay. Yeah, this is the final slides. So yeah, there are further issues that we would like to handle in the near future. For example, we would like even weaker conditions on the structure so that our approach can be applied to more general scenarios. And moreover, how about the non-stationary case? Can non-stationary provide us further information? For example, Quinn just showed a work by Jeff Adam, which is for the non-stationary case, and the structure conditions in the non-stationary case can be milder. And furthermore, how can we, for like more general or domain-specific cases, how can we learn the anti-causal structure? Okay, that's all. Thank you so much.
So we may, let's see whether you have questions, quick questions. By the way, thank you very much for getting up so early in California to educate us. Thank you.
Thank you.
Is the code for the simulation results available anywhere on GitHub?
Is the code available? No, yeah.
We will release the code very soon. Yeah.
Just email Xingshuai right here, Xingshuai Zhong or BW. They can share source code with you, and very soon it will be available. Actually, it's not going to be part of Causal Learn. We are going to have a new packaging with focusing on latent variables. Yeah. Is that fair, BW?
Yeah, definitely.
Hi, thank you. I have a question. If you can go back to one of the decks that you have.
One of the decks?
Hierarchical one.
This one?
Yeah, sure. In this case, do we really need L1 in here? Can we really identify L1? Like, I feel like this latent structure can be reduced, maybe.
Yeah, that's a very good question. So you mean that if we remove some latent variables, it may not affect our results, right?
Yeah.
Yeah, that's a very good question. Actually, yeah, basically we have some graphical constraints on the latent graph so that we can claim that we can find the unique graph. But in some cases without constraints, for example, suppose AR6 only has if it only has one observed children, then in this case, we cannot, the AR6 can be removed as well if AR6 only have one measured children. And it will not affect the rank over the measured variables.
Wonderful. Let me just put it in a slightly different way. You are totally right. However, in this example, the condition holds true, so you can determine L1. There do exist other situations where the graph can be simplified. So here I have a condition, and we will show the slide. Bill, can you go to the slide with the conditions?
Yeah, sure.
You can see right here the condition holds true. Then you have the guarantee that the graph can be recovered.
Yeah.
Oh, I got one question. Thank you for the delivering the speech. So for the future work that you said that you want to generalize the combining both the latent variable and observation data. So it have a potential that this will cause a circle at this moment. So if we are using this model, do you actually need to consider about the time? And since it have a circle, it may have a time sensitive problem. Did you consider about that, or you actually use some kind of condition to avoid the circle situation? Cycle. Sorry.
Thank you for the that's a very good question. So currently we assume it's a DAG, but you're right, it's our next step that also cover cycles. And maybe you have already learned from Professor Quinn's lecture that the cyclic case is harder than the acyclic case. So the cycle, this case will be our next step. Thank you.
As an extension, Bill, let me add one sentence here.
Yeah, sure.
So Shuyan, Peter's student, actually has been trying to extend the result in the linear non-Gaussian case, which I will talk about in 20 minutes, to the situation where you have cycles among the latent variables. And similarly here, you can still do something. But in general, handling cycles in the linear Gaussian case is harder than in the non-Gaussian case. So that's, yeah, good one.
So what's the identifiability condition for the extension work? Is the same as the previous one?
That's a very good question. So basically here, for the latent variables, so we have the same identifiability condition for each latent variables here, but we don't have we don't need any assumptions on the observed variables. And actually, this can be further weakened by use other techniques besides beyond the rank constraints.
So basically, it's almost the same as before, although the situation is much more general, and more specifically, you can just talk to the guy behind you to see more detail.
I have one more question. So if you at first you assume there's no causal directions between the measured variable, and then you extend that. I'm wondering if you use the same data set, would your data structure be different? And in the first case, if you do not assume any causal directions between the measured variable, and then in the extension you do, can I interpret this as saying that you explain some of the causal directions between the measured variable as associations in the first case? That's it.
Did you hear the question?
So actually, I didn't quite get it.
If you want me to interpret, maybe you want to repeat it?
Yeah. So my question is, I'm not sure if you are using the same data set for the first case where you assume no causal directions between the measured variable, and in the second extension where you do assume causal directions between the measured variable. I'm interested to know if you are using the same data set, the data that you would derive would be different even on the same data set. I'm wondering, in the first case, since you do not assume any causal directions between the measured variable, but in actuality there might be. So are you explaining some of those causal directions through associations, through the confounder, through confounders?
Yeah, that's a very good question. Actually, so Xinxuai, what you apply both methods to these big 5 questions. And he found that when we consider the influences between observed variables, it gives us more meaningful results, more reasonable results. Yeah, maybe you can ask Xinxuai for more details about that.
You can talk to this guy. A very quick response as follows, before you give the evidence. You're totally right. If you don't allow edges among the measured variables, you can still get the representation in which you don't have those links, which is consistent with the truth. For instance, in your case, you can just go to the previous the graph with links among measured variables right there.
Links among the measured.
So here, for instance, you can discover the causal link set from x3 to x13. By the way, next time, make sure the variable is not so ugly, x13 to x1. So right there, you can see the causal link from x3 to x13, right? If you don't allow, right here, have a causal link between measured variables, right? If you don't allow that, you are going to see that, generally speaking, x3 and x13 are in a cluster with a single latent variable. And this is a special case because that latent variable can be x3, right? So that's why it's redundant. But Xinxuai, or maybe you can talk. Would you add something here?
Yeah. So for the simulation data, we have test both cases. The first is that where we allow measured variables to have link between each other, and another case is that we do not allow. So we compare both cases. And for the real life data, as shown in the big 5 data set. So basically, we apply both methods, and the results actually is quite similar, except that some measured variables actually should have link between each other. Yeah.
Here. All right.
I mean, the real data set we don't have ground truth, so we just invite some psychological expert to analyze data. So yeah. So maybe we can talk after. Yeah, thank you.
This study was recently done by Dong or Xinxuai, so you can figure out more details with him. Essentially, there are no conflict, so it's just another way to put the final result. You have to introduce a latent variable. Okay, any other questions? It's quite long. If there are no other questions, let's thank you very much, Biwei. Thank you.
Yes, thank you, Kun.
Break. Come back at 11:15.
Yes, thank you. Okay, good. I hope you enjoyed that part. So now let's try to go further. Remember, in that case, I mean, thanks to Xinxuai right there, Biwei and others, we can really discover this, the whole graph in the linear Gaussian case, even if you have latent variables everywhere, right? But first of all, in that case, you can only recover the graph up to the equivalence class. Remember, you can only find this structure, then it will stop. How can you go further? Let me talk about one particular way so that we can really discover the whole graph. So now we focus on the linear non-Gaussian case. And after that, Yijia will quickly share something about nonlinear cases. And I would say, again, the picture is not complete, right? There could be a lot of other interesting works. But for now, in the linear case, I would say it's rather complete. In And in the nonlinear case, very quickly, you can see a lot of new works done by Yujia and others. Okay, let's look at the linear non-Gaussian case, where we assume the causal model again is linear, and that the noise terms are non-Gaussian, even if you have a lot of latent variables. Okay, remember linear independent noise condition. Here, Z causes Y. Suppose Z is a complete set of parents of Y, and then the regression residual of Y on Z will be independent from Z, right? Because in the structural equation model, Y is the function of Z and independent noise. Now just recover it, right? So this is independent noise condition, and you can find order this way. And once you have the order, you can estimate graph. Good. So with the independent noise condition, it's so simple. It's a pairwise thing. You can check for it. You can find the causal order, and you can even estimate the whole causal model by further making use of minimality. And by minimality, I mean sparsity. If it's not necessary for you to have this guy as a parent, then you just cut off the edge, right? What if you have latent variables? Let me give one example to illustrate one thing. Here, look at this example. This is the whole graph. I only consider part of it. And then right here, you can see we have a causal influence from L1 to L2, right? Now you want to determine the direction. Suppose you already know, oh, here I have latent variable, here I have another latent variable. Suppose you want to find the direction, okay? Do you think there's any information you can make use of to find the direction? Any idea? Can you determine, in other words, can you distinguish between this and that case? This case right here, L2, L1 go to L2, and in that case, L2 go to L1. Can you distinguish between them? Clearly in the linear Gaussian case, you cannot. That's why just now, right? We could just end up with the equivalent class. Now, can you? Any idea? If, say, they are measured variables, if L1 and L2 are measured variables, in a non-Gaussian case, can we just say it? Yes, right? Independent noise condition. I know from the wrong direction, we cannot find independent noise. Why? Because thanks to the Darmois-Skitovich theorem, as long as the two variables share the same non-Gaussian component, they will be dependent. That's it. Okay, now you are going to see that even if there are latent variables, almost the same thing will hold true. In this case, basically L1 goes to L3 via L2. So in the transitive, for simplicity, you can assume there's a direct link from L1 to L3. It's the same thing, right? It's the same thing because that's transitive. Okay, so this is the case, first case, and then you can see the following thing. In the first case, you can find a linear combination of x2 and x3 right here, which is independent from x1. You can find a linear combination of x2 and x3, which is independent from x1. I will see why. I will explain why, but for now, I just try to make sure we understand. You are thinking about it, right? Can you imagine that we can find a linear combination of x2 and x3 right here that is independent from x1? Clearly, it's possible. Why? Because they share only a single latent variable. I can find a way so that L1 cancels out in the combination. For instance, I can use right here, we have BC. I can use C times x2 minus B times x1, x3. Right there, here we have causal coefficient BC. Now I get C times this one minus B times this one. Then L1 will disappear. Is that right? If L1 disappears, then this linear combination will be independent from x1 because originally they are related only via L1. Now that guy disappears. Clearly, this linear combination is independent from x1. This is something like independent noise condition. Remember, in the independent noise condition formulation, you have residual, which is a particular way to derive linear combination of y and z, right? Residual is a linear combination, which is independent from the predictor. Now, Yes, I have a linear combination of, again, measure the variables that is independent from x1. And you can easily find the CB, the ratio of C to B. Why? Because, oh, how can I remove this part? I think, give me one second. I see what to do. Ratio high here. I don't know why this part is always there. Hide self view. No. Okay. While you're working on it. So right here, can you find the ratio? As long as you find the ratio, you can find a linear combination to satisfy that condition, right? Can you? It's so easy because you can see the ratio of B to C is nothing but the covariance between 1 and 2 to the covariance between 1 and 3. Why? Because covariance between 1 and 2 would be A times B times the variance of L1. Covariance of 2 and 3, 1 and 3 would be A times C times that variance of L1. If you consider ratio, wonderful. If you consider ratios, cool. Now you can see it's just a B to C. Good. Now you can see in the first case, you can easily find the linear combination determined in a very simple way, which is independent from that guy. Now, in contrast, you can see we cannot in this case. Why? In this case, you cannot find the independent combination of 2 and 3 that is independent from x1, because here, in any case, you cannot find a way so that L2 disappears. Even if L2 disappears right here, you cannot find this one so that L2 disappears. You cannot find it. As a consequence, any linear combination of x1 and x3, any linear combination will have the contribution from L2. Okay, and clear x1 also has a contribution from L2. They share some non-Gaussian component. As long as they share non-Gaussian, we know they cannot be independent. So you can easily show that. Again, this is implied by Damois-Skitovich theorem. Okay, good. Yeah.
Yeah, still don't try to understand, like in this case, why do we need L2 here?
Why do you need L2 here?
Yeah.
By that I mean, you can reduce, okay, without L2, how can you represent the relationships?
Like if we're conditional on L1, then there's no association between x1 and x3. Same as if we're conditional on L2, there won't be any association between x1.
Yeah, totally right. You're talking about the conditional independent relations.
Yeah.
Basically, if you have a linear Gaussian case, that's all the information you can make use of.
Right.
Now you can go further. This information cannot be characterized by conditional independent relations. That's why you can do it. In the linear Gaussian case, forget about it. They are symmetric. In the linear Gaussian case, they are symmetric. But in the linear non-Gaussian case, they are not. Just because right here, yeah, okay. And furthermore, now graphically speaking, you can see the difference. In this case, there exists a common cause or set of common cause of x2 and x3, red variables, which can separate or deseparate x1 from them, right? L1 is the common cause of 2 and 3, and this common cause separates x1 from them. As a consequence, I can do the following because I can remove the effect of this common cause. Then the linear combination and x1 become independent. Remember that. And right here, it's not possible because the common cause of x2 and x3 will be L2. Condition on this guy, they are not separated because of this part. Right? So this is the graphical condition. You can, from the graphical condition, you can easily discover causal direction between the latent variables. Now I know, oh, right here, if I cannot find this condition, I know, oh, clearly this guy cannot go this way, and there must be some guy here as a common cause for them. Okay, now we should basically just need to apply this one. So we formulate the condition. This is a generalized independent noise condition because still it involves combinations of the measured variables. basically is formulated as follows: Z and Y order the pairs. Order the sets of variables. Z and Y follow the gene condition. If there exists non-zero combination Y, which is independent from Z. Here we define W this way because this is just one way to quickly figure out what value you can use for W. That's it. Why can we do so? It's because if they are independent, they must be uncorrelated. Then we can by making sure they are uncorrelated, you can find the value of W, and then you can see whether they are really independent. Okay, so that's the idea. And this is a graphical condition. I just mentioned a graphical condition. As you can see from here, this is Y, this is Z. From this graph, can you see whether Z, Y, the ordered pair, follows the gene condition? Yes, right? Because here I have, for Y variables, I have two latent variables, and then I can find a linear combination to cancel them out. And then the linear combination will be unified from S4 and 6, right? Graphically speaking, you can see the latent common cause of Y variables right here will be L2, L3, L1 and L2, and L1 and L2 can de-separate Y from Z. Condition holds true. Okay, so you can just verify such conditions, and then you can do two things. First of all, you can find the clusters. You can figure out which variables, measured variables, are in the same cluster, meaning that they share the same latent causes. As you can see from here, we have cluster 1, 2, 1, 2, 3. And second of all, you can determine the causal orders of among the latent variables, as you saw from the picture I gave 2 minutes ago. You can really find the causal asymmetry between the latent variables. And then if needed, you can go further. You can estimate the parameters, like coefficients. And it's also done by Xinfei. We can also estimate coefficients if needed. Okay, it's done. And right here you can see application. I will skip the details. You can find the clusters by checking the conditions, and then you can find the orders. Here you can see one application. We analyze the teacher's burnout data. You can see in the data set there are 28 measured variables. As you can see from here, they are measured. And this is a hypothesized model given by experts. They know kind of how education, they understand how to do education. They understand why, as teachers, right, we behave in different ways. That's why they have this hypothesized model, as you can see from here. We just analyze the 28 measured variables right here. We have so many latent variables, and we have clusters, and also we have the code orders among the latent variables. They are identical. Okay, so this verifies two things. First of all, the model given by experts is very good because it perfectly explains the data, right? On the other hand, the computational method could be very useful. Without making use of any kind of background information, you just analyze what you can measure, and then you can really recover the underlying process. That's it, right? Okay. Am I going on time? Yes, good. Now, let's see nonlinear cases. Basically, for this part, Ija, please come. Ija will speak for a couple minutes about the nonlinear cases. And once again, this part could change very quickly. So probably in a few years, you can see it's very different. Before that, now Ija is talking about the IID case. Yeah. This is still the IID situation. You have a single distribution. Later, if you have multiple distributions, we can also deal with the nonlinear case. And the setting is very different. Okay. Thank you.
Okay. Okay, thanks. So previously we have already seen that, okay, we have known the formulation of independent component analysis. And we know that, especially in the cause discovery, with or without latent variable, the IC is very important for us to get the identifiability of the result. For example, for the linear non-Gaussian cyclic model, we need to first get the mixing matrix W in order for us to get the unique, like the solution for the causal adjacent matrix. And also previously, we have also seen that the over complete IC is very important if we have like some confounders or latent variables that we need to take off. So in this case, although we are pretty happy, right? We can really take a look into the latent world by just giving the observed variables, but we have like a fundamental assumption. What is it? Is that we assume that our like process is a linear relations.
So although many real world like generating processes are approximately linear, it's pretty difficult for us to believe that, okay, most real world generating processes are exactly linear. So we need to consider the general nonlinear function just in the nonlinear world. So what's the challenge, right? So we can see that it's pretty famous that the nonlinear IC is seriously unidentifiable or even ill-posed without any further assumption. For example, we can see that in that figure, we have like an independent ground truth sources. They are independent of each other. And we have a pretty nonlinear mixture of them. However, we can generate some fake independent solution, which means that they are independent of each other, but there exists no one-on-one mapping between our ground truth and our constructed estimated solutions, which means that it's just a fake solution. So that example is generated by the famous Darwin's construction, which is basically relying on the conditional CDF to construct like fake independent solution. And there also exists a lot of like other strategy in order to generate just independent solution, but just nonsense, right? In the pretty like free nonlinear world. So yes, we can already see that if we just assume the conditional independence, or if we just assume marginal independence, it might be too weak because we can generate arbitrary fixed solutions that are independent of each other, but not correspond to our ground truth. So yeah, it's pretty natural for us to consider putting some additional assumption. For example, what if we just assume that these sources are conditional independence given an auxiliary variable u here? For example, we just assume that the S1 from S1, S2 to Sn, instead of marginal independent, they are conditional independent given an auxiliary variable u. So that auxiliary variable u could be just domain indexes if we have multi-domain data, or could be just like time indexes if we assume some kind of a temporal structure, or even in the maybe like a more direct way, we can just assume some supervision label for these sources, right? So previously we have just like two layers of the variables. We first have our like the hidden sources here, and we are given only our observed variable in order to discover or recover these hidden sources. So this is a purely unsupervised learning test, just as original IC setting. So instead of that, if we introduce some more additional information, like the auxiliary variable u, we assume that, okay, this u can kind of like play a role like for the label of these sources. We transfer the original unsupervised learning test into a weakly supervised learning test, and it's pretty natural for us to believe that, okay, this additional information can be helpful in order to like identify the whole process. So yeah, this is a recent breakthrough, but unfortunately, the auxiliary variable, like the additional information, is not available in all cases. So right now, assuming, yeah.
Right here, you have to assume there are multiple distributions because it's not the ID setting.
Oh yeah, you're totally right. Because so you could just be domain indexes or can be your time index, so it's not ID setting, and we benefit from the change of the distribution. So in that case, as Kun just mentioned, actually we are putting constraint on the sources, on the distribution as well, right? We want to make it to change. We don't have some additional information. So by the way, so in a word, we putting constraint on the S. So what if we can put constraint on the connected structure, right? So essentially we can see that the Jacobian of the mixing function f implies like the connected structure from our sources to observed variable. And if we can rely on them to put some constraint, it might be helpful to us to get rid of the auxiliary variables. So right now, if we just focus on like take a different view by focusing only on the structure instead of distribution, we need to kick on some graphical criterion in order to get rid of some like impossible cases. Why? Just imagine that for now, if we have like two sources that observe the same set of observed variable, if we take a look at their connected structure from these two sources to the observed variable, we cannot distinguish them. Why? Because for now in the nonlinear world, the distribution can provide like a little bit like information. So we need to focus on the structure. And if they have identical structure, we cannot like distinguish them, and identifiability becomes impossible. So we need kind of like a structure assumption just to guarantee the sparsity or the diversity of the hidden connected structure. So here we just put constraint on the support of the Jacobian, the column of them, and we guarantee that for every latent sources here, there exists a set of observed variables such that the intersection of their parent is Si. And for example, as for S1, you can see, here is the Jacobian of the mixing function, which corresponds to the connected structure here. For S1, there exists X1 and X4 such that the intersection of their parents is exactly S1. So in Qt, we can see that it's just like a graphical criterion to make sure that the hidden connect structure is not like identical. There exists enough sparsity or diversity in order for us to make the model identifiable by only taking a look at the structure instead of the distribution. So yeah, we can see that more clearly from that failure cases. If two sources influence the same set of observed variables, there will exist like two columns with exactly identical support, and it's not possible for us to really identify them, really to determine the unique sources based on the structure. And here is like a very quick like simulation result on real world images, like the EMS, which is basically a larger version of the MNIST data. So for each row correspond to an identified factor, which we guess might be correspond to the hidden sources. So from left to right, we just change the value of the identified factor, like that dimension, from like -4 standard deviation to +4 deviation to see the influence of them. And the rightmost column is is heat map of the difference. So from the first row, we can see that it might correspond to the line thickness of the handwritten digit. And for the second row, it corresponds to angle of it. And for third, it corresponds to upperwise. And for the for last row, it corresponds to height of it. So in summary, we can see that although we cannot like access the hidden connect structure of the ground truth generating data, but we can kind of like conjecture that our structure sparsity assumption might hold true for at least some like very simple ME data set. So yeah, right now we're happy that we can really identify the non-EIC without any auxiliary variable and also without assuming any specific function form. Yeah, question.
So in here, all those latent confounders each other.
Yeah, we assume that all hidden sources are marginally independent of each other.
I would question that the angle and the height they could be correlated with each other. But
yeah.
If you have a deeper angle, then the height will also be kind of lower. Just from this
Yeah. Yes, you are totally right. So right now, these interpretations are just from like our humans. So it might not correspond to the like a real semantical meaning, right? So right now we just select the top 4 like factors with the top 4 standard deviation in order for us. Okay, it might be more informative, but we don't know whether that corresponds to angle or not, right? We just guess it, right? You are totally right. It might be independent. Yeah.
As long as we don't talk about it, but that the reason is because the matter is independent of not say it's actually following exactly the same function in the space. So it really for prediction of this project, we have one that we talk about kind of insanity in real time.
Yeah, I think that's a very like insightful point. So actually in our ongoing work, although we are pretty happy, like we can identify the non-EIC in our supervised learning, there exists some fundamental assumption which arise, part of them arise from the original setting of IC. The first one is that, okay, independent component analysis, they assume that the sources or the causes of the observed variable are independent of each other, and which might not be true in like in many real-world generating process. So in our ongoing work, we prove that even though some sources can be dependent of each other, we can still provide guarantee, at least for the remaining independent sources, and which might be pretty helpful. And also, even though our structural sparsity assumption hold true only for a subset of them, we can also provide some guarantee. And also in all these cases, there exists one limitation that we assume that the number of sources is equal to the number of observed variables. But for many real-world cases, like for image or for like photos, we may easily have millions of pixels, and each of them will be an observed variable. But for the hidden concept, it's pretty crazy for us to assume that, okay, there is a million of hidden concept, right? So that is called the undercomplete cases. And for this result, we do not have any guarantee. But for our ongoing work, we have like provide identifiability, or even for the undercomplete case. So I would say that, okay, after that, we can be a little bit confident to really make sure that, okay, there exists some theoretical guarantee in order to take a look into the latent role, even in the nonlinear case, given only is observed in the unsupervised method. Yeah, thanks so much. Very great insight. Yeah. Any further? Okay, that's good.
Questions? And everything clear.
Thank you.
So let me follow up. First of all, those questions were really great. And note that this is just the beginning of this line of research. And first of all, as you just mentioned, in many cases, they are dependent, indeed, right? In our understanding, the meaningful things can be dependent. And that's why previously we tried to find the causally related latent variables, right? They are dependent. And furthermore, basically, according to you, you don't care. You assume they are independent. In many cases, yes. Like if I go back to this slide, you can see even if we have latent variables which are dependent, but eventually you can say everything right there is generated from the underlying independent noise terms, right? So that's also true. However, still, even in that case, you want to find the right set of latent variables which are not which are not necessarily dependent. Why? Because that give you a simple model. And usually on some assumptions, simple model is true on some assumptions. And furthermore, last point, you can show that in some cases, you cannot find independent variables. Especially if you have multiple distributions, you may not be able, there may not exist independent variable to explain the distribution. And I don't think we'll see. Right now, we don't have a result. We have some ongoing work, but probably within half a year, you'll see, yes, indeed, in many cases, you have to incorporate dependence. Otherwise, you cannot recover the truth. You cannot recover any mathematical model that is consistent with the truth regarding how the distribution is generated. Okay, cool. Another point. Remember this picture in BOE's presentation, there's such a picture as an application of the procedure developed by Xin to the psychological data right here. And you can see, in fact, we have direction. We have directions among the latent variables, right? Actually, those directions were also determined by the gene condition, the linear non-Gaussian, under the linear non-Gaussian assumption. So you can really determine the direction. For instance, maybe you can look at one of them, so where the algorithm is and extroversion. Where are the extroversion here? Algorithm is where the algorithm? Oh, yeah, wonderful, yeah. So this part actually you can see in our previous results, we discussed it. So you can see this link. In fact, the personality's dimensions could be causally related. One of them can be the cause of some other variables, latent variables. Some personality dimensions are very stable, right? We developed those things when we were very young, for instance. And then some other dimension could be very sensitive to other factors, their effects, as you can see from here. It's interesting to try to interpret the result. Do you think the underlying kind of personality dimension for agreeableness regarding how you are kind of agreeable to others is a cause of extroversion? Do you believe so? If you believe, and if this is true, it's interesting because if I want to change this part, I may, at least I can control one thing. I can try to learn to be more agreeable to others. And then I will become better in terms of extroversion, right? So if you can really understand the causal picture here, you can really find a way to control, to make the change in a natural way. Good? Yeah, okay.
If I understand correctly, so this is so why we can use a gene.
Okay, good. Okay, same question. Wonderful. I can fact you now. When we say we use we assume that is Gaussian, we mean the following thing. We just make use of the second order statistics. You just make use of covariance. That's all. In practice, as mentioned multiple times, in practice, usually data are non-Gaussian. So you just go beyond the second order statistics, you can make use of additional information. Even if the data is non-Gaussian, you can still make use of the second order statistical information. That's it. When we say it's linear Gaussian, we don't say, oh, see here, the data must follow linear Gaussian distribution. No, that's not the case. You just make use of the second order statistics. That's all. However, of course, if you really care about statistics, let's consider a very simple problem like linear regression. You use least squares, right? You just make use of second order statistics to estimate regression line. You can show that if the Gaussian assumption is really the case, then the estimate would be kind of efficient, would be best. If the distribution is not Gaussian, then this estimate is still consistent, but it might not be efficient. This is something you have to, the price you have to pay, right? But still, you can make use of the Gaussian methods, which rely on second order statistics to solve the problem.
We have answered the question.
Okay, wonderful. Thank you. Any other questions? Good.
I found that really interesting that L5 is
L5.
L5.
Where's the L5? Right here. Yeah, yeah.
I would like have the because in all other cases the data there's no like a collider.
Yeah, but this is quite natural. Why? Because right here, this is a particular sub-dimension of the personality trait to explain openness regarding how open with the new results, right? You have multiple variables related to openness, as you can see from here. You have better understanding. Of course, to answer those questions, you may basically rely on this latent variable and that latent variable together. Now, if you look at the questions, this way we may kind of present too long. So if we go further, but we focus more, we really care about the real problem. So let's just spend another 2 minutes on this problem. So right here, look at the problems. Look at questions. You remember questions, right? Maybe you can explain it. It's right here. You cannot see it. Okay, so right here, I have this one. I have a vivid imagination. Okay, regarding L4, and this one I do not have a good imagination. Essentially, you can see they are clearly related. They are the hidden variable to explain the two things, right? Regarding imagination. Okay, and right here, this L6 is related to I'm quick to understand things. How quick, right? I have difficulty understanding the abstract ideas and so on. It's about how you can understand others or things, right? What's this? This one is this one. I have excellent ideas. I'm full of ideas. That's this L5. Good. When you say you have a lot of ideas, you have excellent idea, what do you mean? You have two factors. You can understand things very well. At the same time, you have very good way to the imagination. That's why it's very natural to have those two guys as causes for this guy. Right? At the same time, you can see actually imagination is quite irrelevant to how you can understand others. They are two rather independent dimensions, sub-dimensions in the space of openness. Good. Now you really have a better understanding of everything. Even for openness, right? Psychologists may say, oh, it's openness. Now you say, no, it's not just openness. Openness has so many dimensions, they are related. If you want to improve one dimension, you have a way, because you know exactly where it is.
What about neuroticism where there isn't a latent dimension?
Oh, sorry, I couldn't hear the first part.
Is that right? It's connected with the observed variables, so there isn't like actually a latent dimension like the psychologists hypothesize. So how do you interpret those relationships in relation to the other latent constructs?
It's about how I try to understand the question. So
yeah, so just neuroticism.
Yeah.
Like right in the big five, they're
Yeah.
assuming that there are these 5 latent dimensions of personality.
yes,
But in the causal framework or causal discovery, like there isn't a latent factor.
Yeah.
Driving neuroticism.
I
So
see.
how does that coincide with the
Wonderful.
psychology theory?
First of all, wonderful question. First of all, this guy can share more information right there. First of all, previously, when we didn't allow this kind of relations among the measured variables, there was, I can show the picture. There was a latent variable here. Okay. 2 minutes, time out. I can show you that picture for n variables. This is the previous version. Can you see the slide? Also produced by that guy. So right here, you can see this is the previous result. And right here for n variable, there's a latent variable. I try to explain the connection. So where's the n? Right here. See, my latent variables, right? And they are basically consistent. However, when you allow them causal connection among the measured variables, then we go to this. This is also a question related to your question, right? If you allow that, then you just refine the result. And what you can see from this new result is as follows. Are you seeing the right one? Yes. This guy right here, N10, this question is so good to measure the underlying dimension. This one is almost identical to the latent variable you care about. They designed this question in such a good way. That's it. Actually, let's look at this question. What's N10? Listen, I often feel blue. Right? So that's really a fundamental thing. It's so close to the underlying dimension. That's why. Is that I can yeah. So you can discover all those things from data. Okay, cool. Any other questions?
So you have this covariance matrix that you find out the rank. Is it possible to use some other kind of related measure instead of this covariance?
Wonderful. The answer is yes. This is also related to how you can go from the parametric case, the linear Gaussian case, the linear non-Gaussian case, to the completely non-parametric cases. You have to find some other way to assess the kind of rank or information bottleneck thing, right? So yes, it's possible. Right now, in the nonlinear case, it's really hard. I will explain why to you later. So you're totally right. A lot of things can be done in this direction. The answer to your question?
Yes.
Okay, cool. So we are running out of time. Probably I have to postpone something to the afternoon, right here. It's fine. They also they really fit into the material in the afternoon. So probably we should stop here. Thank you very much.